These are the resistors that we use for the project. Again, our circuit is a series parallel circuit, so it's a combination of series and parallel resistance. Our first resistor R1 is in parallel with this branch here, but we have a series resistor here, and we have two resistors in parallel. So if you were to redraw the circuit so it looks, so you can more clearly show the relationship between the two resistors, you can redraw it like this, where you can draw these two, they're in parallel. So I represented them here. And then this one is in series with them. So I put it in series with them. And then they are connected, or all of these resistors, the series one here and the parallel ones, they are in parallel with this resistor right here. So I put them in parallel with this resistor. So this would be R1 here. Then we have we have another resistor which is in series with this branch here, and this is resistor R5 here, which is 470. And so we can see that we have a resistor which is in series with all of this right here. So again, for the resistors here, I wrote the value here. I also put the color code right there. So you can see this is purple, yellow, purple, red. So this is going to be 4, 7, and then the third color is the number of zeros or the multipliers, with red represents 2. So it's going to be 2 zeros. So this makes 4,700. And so we have 4.7K. Now the size of the resistor determines the power rating. So this is a 0.5 or half a watt rating resistor. The tolerance on this resistor is gold. So you can see that the color, the foot color is gold here. So the foot color here is gold. The next resistor we have, R2, is a 10K. So again, brown, black. So this is 1, 0. And this tells us the multiplier, the number of zeros. Orange represents 3. So this would be 10,000 or 10K. Same thing here, same tolerance. We have gold on the last band here. And it's still a 0.5 watt. All of them are 0.5 watts. This one is a 1K. It's black, brown, red. So again, 1, 0, and 2 zeros would be 1,000. This one is red, red, red. So it's going to be 2, 2, and 2 zeros. So this makes it 2,200 or 2,200, which is 2.2K. And the last one, yellow, purple, brown, gold. So yellow 4, purple 7, brown 1. So 1, 0. So it's going to be 470, which is 470 ohms.
So we are in front of our power supply, and now we are going to construct the circuit. Again, if you remember what the circuit looked like, we have the power supply coming in here, positive and negative. Then we have one which is in parallel. Then we have one in series here, another one in parallel here, and 2 in parallel. So we can start with these 2 in parallel. Which is going to be our 1K and 2.2K. So I'll take this out, 1K here, and 2.2K. And this 2 needs to be in parallel. So I'll make this the front of the circuit and this the back. So I'll put this 2 in parallel. The last one is 2.2K. So I'm going to put it right here. Alright, so I'm going to put the 1K in parallel with it. So they need to be in the same rows. So I'll put it in the same row. Alright, so they're now in parallel, they're in the same row. Next, we have one resistor in series with them. So this resistor is in series, which is a 10K. So it needs to be in series with the 2 in parallel. So with that, so this is the 10K here. Black, brown, orange. So it needs to be in series. Let's make this one down 1. And make this one down 1. And this is going to be in series. Alright, so now it's in series. And then we have the power supply coming in. So we can bring the power supply coming in here. Positive will be on the side. Let's put the negative here. Alright. So on the negative of the power supply, we have a 470 resistor in series with the negative of the power supply. So I need to go ahead and put this resistor in series. This is the 470. So this is the 470 here. It's going to be in series with the negative. So I put the same row of the negative. And we put it in series. Alright, the last resistor we have, so we need to get a connection from this resistor. So this point here is connected to the positive, and so I need to have a resistor go from the positive, which is this resistor, the positive, so this is all positive here, positive to the end of this series resistor, and it also needs to be connected to this resistor here. So this, at the end of this resistor, I need to connect the positive, and I need a resistor going from this point to the end of the other resistor as well. Alright, so this is my last resistor here, which is going from positive to the, so it's going from here, this resistor here, to the same row with this one. Alright, now instead of leaving my positive right here, since this is connected to positive, I can just come and put my positive right there, so that positive is connected right there, based on our circuit diagram. Then we're missing a connection to connect, we need a jumper to go from here to here. Just like in our circuit here, we have a connection going from here to here. So I just did a small jumper, and put one in the same row here, same row, and we can connect it right there. And that's it, we are done with the circuit. We can now power it up. We can decide, let's go ahead and use 9 volts. So right now it's powered at 9 volts, and of course I'm going to measure all of this so I can give.
Okay, so our power supply is set to 9 volts, and this 9 volts is powering our circuit. Again, our power is coming in here, and this is exactly what you see happening here. Our power is coming in, positive is going to these 2 resistors, and then the negative has for this resistor in series with it. So what we expect to happen in terms of the voltage drops, we expect that when we come in here, we are going to, the voltage across here is going to be the same voltage across all of here, right? So we're going to have some voltage across here, and the rest of the voltage is going to be dropped across here, and then we go back here. So again, we have some voltage drop here, right? We have, so put the plus there. So we have some voltage drop here, and the rest of the voltage is dropped across there. So this voltage, the same will be across here as across all of there. So we have some here and some there, and this should be added up to 9 volts. Now in terms of the voltage on this side, whatever is left here, some of it will be dropped across here, across this voltage, this resistor right here, and the rest is going to be here. So we can have equal voltage in these 2 here. So again, this voltage here, this voltage, and all the voltage there is the same. And it's going to be 9 volts minus whatever the voltage drop is here will give us the voltage there. So now this voltage here will be also split up. Some will be dropped here, and then we have the rest here. And this is what you will see. So I'll first start by measuring this here, and you will see that this one is going to be 9 minus this one. And then if I, again, since this is in parallel with all of this, the same voltage across this resistor is going to be the same voltage across here. Then I'm going to measure the voltage across this resistor here, and then whatever is left is going to be across this one, and it's also going to be across this one. Alright, so we'll do the voltage first, and then the power, and then the current, sorry. So what's my input voltage? Input voltage, so I put my probe on the negative terminal, and negative and positive. So let's bounce it back down a bit. So the total input voltage is 8.90 volts, 8.90 volts, close to 9. If I put my probe in the power supply, 8.90, okay, that's correct. So first I'll start by measuring the voltage drop across this resistor here, like I mentioned. Alright, so this voltage is, make sure it's a solid connection. .125 volts, so 1.125 volts. So again, based on Kirchhoff voltage law, if this resistor is the voltage drop is 1.125, we expect the voltage across this one to be 9 or 8.9 minus 1.125, right? Because again, this is like a series branch here. So let's go ahead and measure it. So 8 minus 1 point something is going to be 7.78, 7.77. Okay, so this is R1, right? Now, since this resistor is in parallel to this whole branch, it means that the voltage across this whole branch is 7 point something. And so now, if we start at 7 here, and we're moving, then we're going to drop some voltage across here. Let's see how much we're dropping here. Across this resistor right here, R2. Alright, so this one is 7.27. So again, if we start with 7 and we drop 7 here, it means that the rest is very small. Alright, so let's see what is left. So if we drop 7 here, it means we have like 1 here or less than 1. So let's see what is left. And this one in parallel. So again, here we have 0.49 left, 0.49. And this one is, these are in parallel, so they're the same. Alright, so okay, now let's find the currents. Okay, to find the current in the circuit, we need to essentially break up the circuit and allow the current to flow through the meter. So first we need to organize, we need to set the circuit, our meter configured to measure current. So we go to milliampere hours, and of course we need to use the milliampere circuit to measure current as well. And now we need to break up the circuit, and we need to allow the current to pass through the meter. So we'll start by measuring the total current. So I'm just going to disconnect the positive and put the positive on this side here, and now I will use the meter as a jumper to go between here and there. So I'm using the meter as a jumper now. Alright, let's go. Alright, so the current that is flowing right now is 2.42 milliamps. That's the total current. So now we can check the current flowing in each of the branches. So this is the total current, 2.42. This is the same current flowing through this resistor right here, because it's a series with everything. So this will be the total current. So now we're going to find what is the current this resistor, and then what is the current, and then what is the current here, and what is the current in each of these. Okay, so to do that, let me turn it. In fact, let me start on this side. So I'm going to just remove one of these guys, legs, disconnected from the circuit. Let's put this back. So we'll do this first. So essentially we just separate the circuit, and then we can use the meter as a jumper to close the circuit. Alright, so this is the current flowing in this resistor here, 0.23 milliamps. Great. Let's do the current flowing in this resistor. So I just shifted the ground here, so same thing, we'll connect this resistor. This one is a little more current, 0.49, almost double, right? 0.49, because this one is 2K, this one is 1K, so we expect more current to pass through the lower resistor. So again, let me put it so you can see. The current is 0.49 milliamps. Alright, let's move on to the next one. Let's go on to this one. So again, we'll see that the current flowing for this one is the total of these two currents. 0.49 and 0.2 is about 0.6. So again, to do this, I'm just going to disconnect this guy here and put it somewhere else. Let's put it in the bus here, because we're not using this bus at all. Alright, so again, we just disconnected the circuit, and we're going to make the current flow through the meter. Let's see if you see anything. So what's the total current? It's about 0.7, which we said 0.2 plus 0.4 something. We have 0.73 milliamps. So we can see that these two currents add up to this current here, which verifies Kirchhoff's current law. Okay, let's move on to the next one, which is the last one. We're going to measure the current flowing in this resistor right here. So to do that, we're essentially going to disconnect this resistor. Let's put it right there. And we're going to use the meter as a jumper to jump between this point here, where we were connected before, and the resistor right here. Alright, so you see the current is 1.68. Now the total current is 2 something milliamps. So again, the total current is going to be 1.68, which is whatever passed here, and then whatever was here was 0.7. So 1.68 plus 0.7 will give us 2 point something. And so, last but not least, the total current we measured before we started, this is the same current that is flowing through this resistor right here. And so just to show you that, I will just disconnect this resistor, and we'll use the meter as a jumper to go in between this resistor and ground. And so the total current is 11.7 milliamps. So this is the total current, 11.7 milliamps. Okay, hold on. Oh, sorry. Okay, so this was not correct. I think this was touching this signal was getting energy from this terminal. So let's measure it again. So this is the correct current. It's 2.42 milliamps. 2.42 milliamps. All right, that's what you need.
So I'm going to show you a little of the simulation, how you would simulate your circuits in Multisim. We did a tutorial before, but I decided to just demonstrate this one to show you how you would collect data from a simulated combination circuit. So first step would be to select the resistors and to place the resistors, and then to change the values of each of them. So again, I have my R1, R2, and R3, and we have R5. And then I'm going to go ahead and select the DC source and also a ground as well. And the next step is to connect the circuit and then to change the values. Afterwards, after we have done that and we have all the correct values, then we are going to go ahead and add the measurement instruments so that we can go ahead and measure the circuit. So on here, I'm just going to put some sample statements so that students can copy this work and submit it as their own. I want you to go and use Multisim and simulate your own circuit and provide this, in your lab report. Okay, so now I'm going to just start changing the values. So this should be 470. And this one at the front here should be 4.7K. Alright, now we add the instruments. So again, we're measuring the voltage across the resistors, so it's the differential voltage. So I add those in, and then I'm going to add the meter to measure current in each branch. Alright, so again we have the total current, then the current splits up here, and so we find the current in this branch and the current in that branch. Then the current splits up here again, so we want to find the current in each branch. And so then the last step is to hit the simulate button. And of course we mine the current in this branch as well. Now it should be the same as the current at the top here, which is the total current. And we can see that when we look at the simulation, we can see that we have a total voltage drop in this resistor or the total current here is the same as the one at the bottom. We also can see that we have a total of 9 volts, and so if we drop 7.8 here, then whatever is left is going to the same voltage will be across here. So we actually will drop 7.3 volts across there, and so the voltage across the parallel branch is going to be about 0.5 volts. Again, the current, this part of the circuit at the front is series, so we have current in the current at the total current is the same amount that passes through this 470 ohm resistor. Likewise, the current splits up and passes through the parallel branch, so that if you add these two currents, they should add up to the current going into the parallel branch. Okay, that's it. I hope to see your results in your lab report. And that's it for this simulation exercise, and hope that it was beneficial to you. Thank you.
Hello, Gecko. Hello, Moto. How you doing there? Happy Sabbath.